Please pause the video and try this problem. Now, let's discuss the problem together. Remember, if you find that these video explanations move too slowly, you can simply try the problems in the problems document, study the solutions in the solutions document, and, if necessary, use the table of contents for each video to skip to the particular parts of the videos that cover the parts of the solutions that are giving you difficulty. Here are some YouTube controls which you may find useful while you're watching the videos. Here's a summary of the solution for part A of the problem. Now let's discuss this solution step by step. After it leaves the plane and before it hits the ground, the only force on the package will be the force of the Earth's gravity. So, the package will undergo projectile motion. Draw the package's path of motion. The general path for two-dimensional projectile motion is a parabola. Since the package is already moving downward when it is released from the plane, for this problem, the initial slope of the parabolic path should be downward, at an angle of 25 degrees below the horizontal. Let's call the instant when the package leaves the plane t sub 0, and let's call the instant when the package hits the ground t sub 1. For projectile motion problems, it's usually best to choose up and right as your positive directions. During the interval of projectile motion, this will be the package's furthest left position, and this will be the package's furthest down position. So let's choose this point as the origin for measuring position. Write down the coordinates for position for each of the key points in time in your sketch. When possible, write down a specific value for each coordinate. So far, we don't know the horizontal location of the position at t sub 1, so we will continue to use the symbol x sub 1 to represent the horizontal coordinate for this position. Part A asks us to find the horizontal distance between the release point and where the package lands on the ground. We can build that question into the sketch, like so. Because x sub 0 equals 0, this horizontal distance will be equal to x1. So we can use the symbol x1 to represent what the question for part A is asking us for. The problem tells us about the velocity at time 0. So let's draw the velocity vector at time 0. The velocity vector at time 0 is drawn tangent to the object's path at time 0. The problem tells us that when the package is released at time 0, the plane is moving with a speed of 90 meters per second at an angle of 25 degrees below the horizontal. Before time 0, the package is being carried along in the plane. So, at time 0, the package's speed and direction of motion will also be 90 meters per second at an angle of 25 degrees below the horizontal. Remember that speed represents the magnitude of the velocity vector, and the object's direction of motion tells you the direction of the velocity vector. Now we need to break this velocity vector into components. Here's a summary of the method for breaking the velocity into components. The overall velocity vector points down and right, so the components point down and right. Right is our positive x direction, so v sub x is positive. Down is our negative y direction, so v sub 0y is negative. We label the 25-degree angle with an asterisk to indicate that in our SOHCAHTOA equations we plan to use the 25-degree angle rather than using this 65-degree angle. This side is labeled as hypotenuse because it's across from the 90-degree angle. This leg is labeled as adjacent because it's adjacent to the angle we marked with the asterisk. This leg is labeled as opposite because it's opposite to the angle we marked with the asterisk. Our results are that the magnitude of v sub 0y is 38 meters per second, and the magnitude of v sub x is 81.6 meters per second. Now, we use absolute value symbols in our SOHCAHTOA equations because the SOHCAHTOA equations can only tell us the magnitudes of the components. It's our job to determine the plus or minus signs for each component in a separate step. Like so. We already decided earlier that v sub x is pointing in the positive x direction, so v sub x is positive. And we decided earlier that v sub 0y is pointing down, which is our negative y direction. So v sub 0y is negative. It's crucial to include this negative sign in front of v sub 0y. If you leave out this negative sign, you will get the problem wrong. I recommend that you should make it a habit to include plus signs in front of positive components, such as v sub x for this problem, because that will help you to notice when you need the crucial negative signs in front of negative components. Now let's build these results for the components into our sketch, like so. Let's label t sub 0 and t sub 1 as our initial and final points. Now we're ready to create the projectile motion setup, and then to work with the kinematics equations. Here's how we begin the setup for a projectile motion problem. In your setup, indicate the question with a question mark. We've determined that when we know x1, that will tell us the answer to the question, and we're treating x1 as x final. So we put a question mark above x final in our setup. So our plan for this problem is to use the setup for the y component to determine delta t. Then we will substitute our result for delta t into the kinematics equation for the x component. Then we will use our equation for the x component to determine x sub 1. Now, based on the work we did in our sketch, we can write down specific numbers or symbols for each of the variables in our setup, like so. We still have two unknowns in our x equation, x sub 1 and delta t, so we're not ready yet to solve the x equation. When you know values for 4 of the variables in your setup for the y component, you're ready to choose a kinematics equation for the y component. We do know 4 values for the y component: y initial, y final, v initial y, and a sub y. So we are ready now to choose a kinematics equation for the y component. The quickest way to choose a kinematics equation for the y component is to identify the kinematics variable that we do not care about. We care about these 4 variables because we know their values. And we care about delta t because we're planning to substitute our result for delta t into the kinematics equation for the x component. So for part A, the kinematics variable that we don't particularly care about is v final y. So we choose the kinematics equation that's missing v final y. That's this equation. Be careful to include the crucial negative signs when you substitute for v initial y and for a sub y. Our kinematics equation now has one unknown, delta t, so we can now solve this equation for delta t. Now, this is a quadratic equation with 3 terms. A term with delta t, a term with delta t squared, this is the term that makes the equation quadratic, and a term without delta t. To solve this type of quadratic equation, we need to use the quadratic formula. To use the quadratic formula, let's rewrite this equation so that it matches this general form, like so. Notice that I've written this term as an addition rather than as a subtraction, so that it will match the addition in the general form. Now we can identify the values for A, B, and C, like so. Be careful to get every sign correct. Our value for A is negative 4.9. Our value for B is negative 38. Our value for C is positive 150. Now we're ready to use the quadratic formula. First, write down the general quadratic formula. Then substitute specifics into the formula, like so. Be careful to include all the necessary minus signs. The quadratic formula has a negative sign here, and our value for b is negative. So here we initially write 2 negative signs. The quadratic formula has a subtraction here, so here we write a subtraction. Our value for a is negative, so we write a negative sign here, and we write a negative sign here. Take your time and be careful to get all the minus signs correct when you use the quadratic formula. Now I'm going to discuss how to do this calculation on your calculator. If you thought it was easy to do the calculation on your calculator, you can use the table of contents to skip ahead. Before we do the calculation on our calculator, we can make some simplifications. A negative of a negative is a positive, so these two negative signs cancel each other out. The square of a negative is a positive, so this negative sign cancels out. Subtracting a negative is the same as adding a positive, so these two negative signs cancel out. If your calculator has a fraction template, then we can perform this entire calculation in one step on the calculator. Here's how that would work on a TI-84 Plus calculator. To access the fraction template on a TI-84 Plus, we hit the alpha key. Then we hit the y equals key. Then, to select the first fraction template from this menu, we hit the enter key. Now, enter the calculation in the calculator so that it looks exactly the same on the screen as it does on the page. This symbol stands for plus or minus. Let's begin by entering the symbol as an addition sign on the calculator. Now, to move the cursor to the bottom of the fraction template, we hit the down arrow. Before you hit enter, double check that the calculation looks exactly the same on the calculator screen as it does on the page. When you've done that, you can hit enter. Our result is that delta t equals negative 10.6 seconds. Now, delta t stands for the time that elapses before the package hits the ground. Time elapsed can never be negative. So we need to throw out this result. That's okay, because we remember that this symbol can stand for either plus or minus. So we need to redo the calculation on the calculator, this time with a subtraction at this point. I use the up arrow to go back to the previous calculation. I hit enter to retrieve that calculation. Now I use the arrow keys to move around in the calculation. And I position the cursor here where we need to make the change. And we need to change this addition into a subtraction. So I hit the subtraction key. And now we've made the change that we needed to make. Don't confuse the subtraction key with the negative key. In this position, we wanted a subtraction. So in this position, we used the subtraction key. In contrast, in this position, we wanted a negative number. So in this position, we used the negative key. Now we can hit enter. And our new result is that delta t equals 2.88 seconds. This result is positive, so this result for the time elapsed does make sense. Now, how do you perform this calculation on a calculator that does not have a fraction template? I know that the way most students would do it is to break up this big calculation into a bunch of smaller calculations. If you're careful, that method will get you the right answer. But as an alternative, I'd like to show you how you can do this calculation on your calculator in one step, even without using a fraction template. If you're not interested in this information, you can use the table of contents to skip to the next topic. We can use these rules to perform a calculation in one step on a calculator that does not have templates. This method will involve adding some parentheses. Now, we already have a bunch of parentheses, and if we add even more parentheses, the expression is going to look very confusing. So, before we add the necessary parentheses, let's remove some unnecessary parentheses from our expression. Like so. I've rewritten the multiplications with asterisks, because that's what the multiplications will look like when we enter them in the calculator. Now let's add the necessary parentheses. Based on this rule, we need a parenthesis here to tell the calculator where the numerator begins, and we need a parenthesis here to tell the calculator where the numerator ends. Based on this rule, we need a parenthesis here to tell the calculator where the denominator begins, and a parenthesis here to tell the calculator where the denominator ends. Based on this rule, we need a parenthesis here to tell the calculator where the inside of the square root begins, and we need a parenthesis here to tell the calculator where the square root ends. This exponent contains only one number, so we don't need parentheses around this exponent. Now we're ready to enter the calculation in one step on our calculator. I'll demonstrate this process on my TI-84 Plus calculator. First, in order to turn off the template function, I will switch the calculator to classic mode. That turns off the template functions on this calculator. Now I slowly enter the calculation in the calculator, exactly the way I have it written on the page. We start with a left parenthesis to let the calculator know that we're beginning the numerator. 38. I will begin by interpreting the plus or minus symbol as an addition. Square root. You can see that in classic mode, the TI-84 automatically puts in this left parenthesis after the square root to indicate the beginning of the inside of the square root. 38 squared plus 4 times 4.9 times 150. Now we enter a right parenthesis to indicate the end of the square root. And then we enter another right parenthesis to indicate the end of the numerator. Divided by, don't forget this divided by symbol, left parenthesis to indicate the beginning of the denominator, 2 times negative 4.9. Right parenthesis to indicate the end of the denominator. Before you hit enter, double check that the way the calculation is entered on the calculator matches the way you have it written on your paper. Now we can hit enter. Our first result is negative, and time elapsed cannot be negative. So we throw out that result and redo the calculation. We use the arrow key to go up to the previous calculation, enter to retrieve that calculation, and we use the arrow keys to move over here, and we're now going to change this addition into a subtraction. And now we can try the calculation again. Our result is that delta t equals 2.88 seconds. If you regularly work with a calculator that doesn't have templates, then you should pause the video and memorize these rules for doing calculations in one step. The key to doing a calculation correctly in one step on your calculator is to write the calculation on the page exactly the way you want to type it on the calculator before you actually enter the calculation on the calculator. We've used a kinematics equation for the y component to determine that delta t is 2.88 seconds. Now, we substitute this result for delta t into our kinematics equation for the x component. This equation now has only one unknown, so we can now determine the value of x sub 1. Our result is that x sub 1 equals 235 meters. Build your results for delta t and x1 into the sketch, like so. Now, we're ready to answer the question for part A. The question for part A asks for the horizontal distance between the release point and the point where the package lands on the ground. We found that x1 equals 235 meters, and x sub 0 equals 0. So, the horizontal distance from here to here is 235 meters. So the answer for part A is 235 meters. Now we're ready to work on part B of the problem. Here's a summary of the solution for part B, and now let's discuss this part of the solution step by step. These question marks in our sketch refer to the question for part A, which we've already answered. So let's erase those question marks for our work for part B. Now we're ready to identify what the question for part B is asking us for. Part B asks us for the package's speed when it hits the ground. The package hits the ground at time t1. The speed is the magnitude of the velocity vector. So, part B is asking us for the magnitude of the velocity vector at time t1. When possible, represent what the question is asking you for with a symbol. We can use the symbol v sub 1, written without an arrow on top, to stand for the magnitude of the velocity at time t1. Remember, when we write a vector symbol without an arrow on top, the symbol stands specifically for the magnitude of the vector. When possible, build the question into the sketch. The question for part B is asking about the magnitude of the overall velocity vector at time t1. So let's draw that velocity vector. The velocity vector at time t1 should be drawn tangent to the package's path of motion at time t1. Tangent to the path of motion at time t1, like so. The question is asking us for the magnitude of this vector. After it hits the ground, the package will be at rest, so its speed will be 0. But it doesn't seem likely that the professor wants us to answer 0 for part B. So for part B, we will think of time t1 as the last instant that the package is moving through the air, rather than as the first instant that the package is resting on the ground. You can see that we know everything there is to know about the package's velocity at time t0. But what do we know about the package's velocity at time t1? Remember that in projectile motion, the vertical velocity is changing, but the horizontal velocity is constant. Since the horizontal velocity is constant, we know that the horizontal velocity at time 0 will be the same as the horizontal velocity at time 1. So we know that the horizontal velocity at time 1 will still be positive 81.6 meters per second. Always try to use the exact right symbol. Use the same symbol for things that are equal. Since the horizontal velocity is constant, we can use the same symbol, v sub x, to represent the velocity at time 0 and at time 1. On the other hand, the vertical velocity will be changing, so we do not expect the vertical velocity at time 1 to equal the vertical velocity at time 0. Use different symbols for things that are unequal. Since the vertical velocity is changing, we use two different symbols, v sub 0y and v sub 1y, to represent the vertical velocity at time 0 and at time 1. We can see now that in order to determine the magnitude of the overall velocity at time 1, we will need to determine v sub 1y, the y component of the velocity at time 1. Now let's update our kinematic setup. This question mark indicates the question for part A, so we can erase that question mark for part B. We just decided that before we can answer the question for part B, we will need to determine the y component of the velocity at time 1. So, in our kinematic setup, we write the word need over the variable v sub 1y. For part B, we will continue to treat t sub 1 as the final point. So v sub 1y will represent v final y. In part A, we found that delta t is 2.88 seconds. So now let's build that information back into our setup. We now know all of the kinematics variables except for v final y. So there are now two different kinematics equations that we could use to find v final y. We can use this equation, or we can use this equation. We can't use this equation because it's missing v final y. This equation is simpler, so let's use this equation. First, we write down the general equation. V final y equals v initial y plus a sub y delta t. Then we can plug specifics into the equation. For delta t, we plug in the value we determined in part A, 2.88 seconds. Be careful to include the crucial negative signs on v initial y and a sub y. This equation now has only one unknown, so we can now determine the value for v sub 1y. Our result is that v sub 1y equals negative 66.2 meters per second. Does it make sense that our result for v sub 1y is negative? The negative y direction is down, so our negative result indicates that the package's vertical motion at time 1 is downward. Based on this path of motion, we expected that the package's vertical motion at time 1 would be downward. So yes, it does make sense that our result for v sub 1y is negative. Let's build this result into our sketch, like so. We now know both the x and the y components of the velocity at time 1, but the problem is asking us about the magnitude of the overall velocity vector at time 1. So now we will need to use the components of the velocity at time 1 to figure out the magnitude of the overall velocity vector at time 1. I discussed how to use components to figure out the magnitude of the overall vector in my earlier video series on vector components. First, let's redraw the overall velocity vector at time 1, like so. Now let's draw a right triangle to represent the components. In this problem, we chose horizontal and vertical axes, so our right triangle should have horizontal and vertical legs. The overall vector points down and right, so the components point down and right. We know that v sub x is positive 81.6 meters per second. The result we figured out for v sub 1y is negative 66.2 meters per second. The question is asking us for the magnitude of the overall velocity at time 1. We can use the Pythagorean theorem to find the length of the hypotenuse of the right triangle from the lengths of each of the legs of the right triangle. Our result is that the magnitude of v sub 1 equals 105 meters per second. We can build that result back into our sketch. Now we're ready to answer the question for part B. Our answer is that the package's speed when it hits the ground is 105 meters per second. Now let's ask whether our results make sense. Does the magnitude of our result for x sub 1 make sense? Well, the horizontal distance of 235 meters is comparable in size to the initial vertical height of 150 meters. So yes, I do think that the magnitude of our result for x sub 1 is reasonable. Does the magnitude of our result for v sub 1y make sense? Well, it's interesting to compare the magnitude of v sub 1y, 66.2 meters per second, with the magnitude of v sub 0y, 38 meters per second. Does it make sense that the magnitude of v sub 1y is bigger than the magnitude of v sub 0y? The package experiences a downward pull from gravity. So, as the package falls from the plane, we expect that the package's vertical speed will increase. So yes, it does make sense that the package's vertical speed when it hits the ground will be greater than the package's vertical speed when it's released from the airplane. Now let's do a recap of our work on this problem. To solve this quadratic equation, we had to use the quadratic formula. Before you use the quadratic formula, identify your values for a, b, and c, like this. Be careful to get the right signs for a, b, and c. We discussed how you can perform the calculation for the quadratic formula in one step on a calculator with fraction templates. And we discussed how you can perform the calculation for the quadratic formula in one step on a calculator without templates. This symbol stands for plus or minus, so you should perform the calculation twice, once as an addition and once as a subtraction. You will usually need to throw out one of your results. You should throw out the result that doesn't make sense in the context of the problem. To be sure that you have mastered this important process, please pause the video and redo this part of the problem. Use the quadratic formula to find delta t. Okay, I hope you tried that. You should again have gotten the result that delta t equals 2.88 seconds. To succeed with physics, think in terms of components. The problem gives us information about the overall velocity vector at time 0. And part B asks us for the magnitude of the overall velocity vector at time 1. But we do not go directly from the overall velocity vector at time 0 to the overall velocity vector at time 1. Instead, first we break the overall velocity vector at time 0 into components. Then we use the velocity components at time 0 to determine the velocity components at time 1. Then we use the velocity components at time 1 to determine the magnitude of the overall velocity vector at time 1. It's crucial to include this negative sign in front of v sub 0y. Remember to include a plus sign in front of positive components like v sub x, since that will help you to notice when you need a negative sign in front of negative components. In projectile motion, the vertical velocity is changing, but the horizontal velocity is constant. So we knew that the horizontal velocity at time 1 would be the same as the horizontal velocity at time 0. You should use the same symbol for things that are equal. So we used the same symbol, v sub x, for the horizontal velocity at time 0 and for the horizontal velocity at time 1. In contrast, the vertical velocity is changing, so we had to use a kinematics equation to determine the vertical velocity at time 1. You should use different symbols for things that are unequal. So we used the symbol v sub 0y for the vertical velocity at time 0, and we used a different symbol, v sub 1y, for the vertical velocity at time 1. If you know the components of a vector, you can use the Pythagorean theorem to find the magnitude of the overall vector, as we illustrated here. The key to succeeding with projectile motion problems is to write down the projectile motion setup, as we've shown here. For a projectile motion problem, the connecting link between the x component and the y component is delta t. In this problem, we used the y component to determine delta t, then we plugged our result for delta t into the equation for the x component. In contrast, for this problem from the previous video, we used the x component to determine delta t, and then we plugged our result for delta t into the setup for the y component. Notice that after we used the y component to determine delta t, we also built that information back into our setup for the y component. Then we used the setup for the y component a second time. The second time, we used the setup for the y component to find the final y. Arrange your work for the x component and your work for the y component in two adjacent columns, like we've shown here. That will help you to keep your math organized. By the way, notice that this is the first video in this series in which we've used this kinematics equation. For a projectile motion problem, build as much kinematics information as possible into your sketch, as we've shown here. For example, we clarified our thinking by building the velocity components at time 0 and the velocity components at time 1 into the sketch. When convenient, build the question into the sketch, like this or like this. Draw a large sketch so that you'll have ample room to clearly include all the information you need in your sketch. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.